So guys, now we are solving one of the problem of DSS2. Now we are designing a purlin. Okay, under purlin we are designing especially the channel section. Okay, there are four things we are supposed to do. Under that, first we are doing the channel section. So whatever the data given, we have to note it down. So the design a purlin on a sloping roof trusses with a dead load of 120 Newton per meter square. Okay, this is given in Newton per meter square. Further, we have to convert it into kilonewton per meter square by dividing it by 1000. Okay, in order to match all the loads in units, and a wind load of 2 kilonewton per meter square. Okay, the purlins are spaced at 2 meters center to center and trusses are placed at 4.5 meters center to center. The purlins are simply supported on the rafters. The span of the roof truss is 20 meters. The pitch of the truss is 1 in 4. Design the purlin providing channel section. So onto the channel section. So this is the sketch of the section. Okay, so this is the channel section. So the 4.5 meters is the center to center distance of the trusses, and this 2 meters is the spacing of the purlins. Now in that, first with the given data, we have to first calculate the UDL due to dead load. So the dead load was given as 120 Newton per meter square. So here what we have done, we have converted as kilonewton by dividing it by 1000. So it is now 0.12 kilonewton per meter square. UDL due to dead load is 0.12 into spacing of the purlins, that is 0.24 kilonewton per meter square. We designate it as W suffix SW. This indicates the dead load. Okay. Now coming to the further steps. So it's been given that the pitch of the truss is 1 in 4. So here pitch is equals to 1 by 4. Now pitch is given by rise by span. Okay, so pitch is nothing but your rise by span, and if now rise can be written as span by 4 meters. Okay, so rise is equals to what is span? 20 meters. 20 by 4 will give you 5 meters. Okay, so this is rise is 5 meters. Now tan, what is this angle? You have 5 and 10 here. Okay, this spacing is 10. And what you can write, tan theta is equals to 5 by 10, which is equals to 1 by 2. Theta is equals to 26.56 degrees. So now we have to divide this dead load, along x direction and y direction. That is, along x it is considered as z direction and y direction. WSWZ is equals to WSW into cos theta along z axis and WSWY along y axis. So it is cos theta and this is sin theta. So the respective values are here. WSWZ happens to be 0.214 and WSWY happens to be 0.107 kilonewton per meter. So now we have to calculate the live load. What is the live load? See, what is the concept for this? Now referring to IS 875 part 2, assuming no load is provided on the roof truss except for the maintenance. See, until 10 degrees, what you can take the live load as 0.75 kilonewton per meter square. But now the slope is more than 10 degrees, that is, it is 26.56. Hence the formula for that calculation of live load is 0.75 minus 26.56 minus 10 into 0.02, which should not be less than 0.4 kilonewton per meter square, but we got 0.41, hence it is safe. Now UDL due to live load is 0.41 into spacing of the purlins, that is 2. We will get 0.82, which is WIW. Okay, this is the live load indication. Now next, now we have to calculate the live load along z axis. Now when we have to calculate live load along z axis, what we will get? WIW into cos theta, that is WIWZ along z axis is equals to 0.8 to 26.56. so what we get? 0.73. Now along y axis it will be WIW into sin theta, so 0.82 into 26.56 into, so we will get 0.37 kilonewton per meter. So this was along z axis and y axis. Now wind load. Okay, wind load, what all wind load was given as 2 kilonewton per meter square. Here you have the wind load in the question, 2 kilonewton per meter square. That is what we have taken into 2, that is the spacing of the purlin. So normal to z axis it will be WWZ, which is equals to WW, because it's the only load along direction it is going to act, because there is no wind load along the y axis. In vertical direction there won't be no wind load. The wind load will be acting horizontally. That is why we have taken WWY as 0. Now load combinations. To understand this, we have load combinations over here. So you can see the load combinations. And the load combination here we have to different bifurcate into two directions, that is z-axis and y-axis. Along z-axis you have three load combinations, that is first one WDZ1 and WDZ2 and WDZ3. Okay, so for the WDZ1 we have this load combination WSWZ plus WIWZ. So this is a partial safety factor. When you multiply you will get 1.416. Now the second load combination is WSWZ plus WIWZ plus WWZ. So partial safety factor is applied is 1.2. When you multiply with the numbers you get 5.93. These all things you have already calculated. Okay, and the third load combination is dead load plus wind load. So you have taken the values belonging to this. You have already calculated this is dead load along z direction and this is wind load along z direction. So you can see all the loads are along the z directions. You can see the last component is ending with z. It indicates that all the loads are taken along this z direction because we are calculating normal to z axis. So here so now WDZ will be the greater of all the three values. The greater of all the three values is how much? It is WDZ3. Now along y direction. Along y direction we have WDY1 is equals to 1.5 into WSWY. This is due to dead load along y direction. This is wind load along the y direction. So you have taken the values which you have already calculated and now you have got as 0.715. And WDY1 will be equals to WDY because there won't be no wind load along the y direction. Hence you have ended the load combination is along y direction as only one combination. So WDY1 will be WDY itself. Okay, after this you can come to this step. Now the load combinations you have direct. Now you have taken those values. WDZ is 6.36 kilonewton and normal to y-axis it is WDY, that is 0.72 kilonewtons. Now because of these loads what you will be calculating? Bending moments. Now design bending moment in the z and y direction. Mz is equals to 6 point, that is you can see WDZ into L span. Okay, 6.36 into 4.5 square divided by 8 you will get 16.9 kilonewton per meter. And you have here My, so it is WDY into L square. So WDY you got as 0.72 into 4.5 meter square. So you have got 1.79 kilonewton per meter. Now after calculating bending moment you will be calculating the shear forces. So this is along z direction, this is along y direction, that is WL by 2. So W will be WDZ and here it will be WDY. Now after calculation of all bending moment and shear forces you will be calculating now trial section. Looking at the bending moment you got, you will fixing up the trial section. So approximate ZPZ required. What is the equation you are going to use? Mz into gamma m0 by Fy plus 2.5 d by b into My gamma m0 by Fy. So here you are assuming ISMC 200 which is having depth as 200 and width of the flange is 75 mm. So taking those values you are substituting and you are getting ZPZ required is around 123.3 centimeter cube. Okay, or 123.3 into 10 raised to 3 mm cube. So referring to this you have to select such a section whose ZPZ is more than the required ZPZ. So you have, once you write this section you have to write all the properties from the steel table and also from the IS 800 2000 okay code book which is used for steel design. So next, after selecting a appropriate section and writing its properties from both the code book and steel table, now you have to go for check for flexure. So in order to check for flexure your design equation has to be satisfied. Okay, so the design equation happens to be mz by mdz plus my divided by mdy should be less than equals to 1. So your mdz, so one of the component, the formula is mdz beta b zpz fy by gamma m0 and 1.2 zdz fy by gamma m0. So here what you are considering, you are considering it as laterally supported. Okay, so in order to finalize your beta b you will have to classify the flange and web sections. Okay, the web, this is flange classification. So b by tf, so your b will be nothing but your width of the flange itself, so 75 by, so it is less than 9.4 epsilon. Now flange belongs to plastic section and now you have to classify the web. What is web? D by tw and your d is nothing but your capital D minus 2 into tf by tw. So here you have to substitute all the values of ISMC 200 and you should see that it should not go beyond 84 epsilon, hence it is less than 84 epsilon, hence your web also belongs to plastic section, hence when both the sections are belonging to plastic, your beta b will be 1. So your mdz, after substituting all the values, you'll be getting 48.01. Next, in order to evaluate mdy, you need a sketch here. So with the help of this, you can calculate. This is the equation to be used in order to calculate mdy. Okay, so and now zey, in order to calculate zey, iyy by x max, iyy you have already obtained it from the table, from the selected section, and your x max is this portion. Okay, this portion is your x max. So what you have your cyy, whatever left will be your x max. That is the value from the soffit of the flange. So how much you get? 26.37 into 10 raised to 3. Okay, that will be your zey. Now looking at the sketch. Okay, now assuming equal area axis lies outside the web as shown in the figure, we are assuming that our equal area axis lies outside the flange, outside the web. Sorry, this is the web portion of your channel section, so we are assuming that it lies outside the web. So how you have to calculate it? X bar is equal to x bar into this 11.4 is the thickness of the flange into 2. There are 2 flanges, 1 and 2, is equals to total area by 2. Okay, the area you will be having from the code book. So area is like 2821. Okay, since 2 flanges, once you calculate that, you will get x bar is equal to 61.86. okay, so that 61.86 is this portion. Okay, this is x bar, and now this is x bar, this is 61.8, and remaining will be 13.2. okay, 61.8 plus 13.2 happens to be total width of the flange, that is 75 mm. So till equal area axis it is 61.8 and the left out part is 13.2. hence whatever you have assumed is correct, that is your equal area is lying outside the web portion. The thickness of the web is 6.1. okay, once you are done with that, you can come to this portion. Now how do you calculate this? You can see here, so zpy is equals to this calculation is of 2 flanges. okay, this calculation is of 2 flanges. You can, what is the dimensions you can take? 61.8. This portion is 61.8. we are calculating of this portion, 61.8 into thickness. okay, into thickness into 61.8 divided by 2. okay, into 2. that is what we have done here. 61.8 into 11.4 into 61.8 divided by 2 into 2. now plus we are calculating the web portion. Now web portion area is 200 into 6.1 is the thickness. okay, into 13.2 minus 6.1 divided by 2. so from here to here, this portion. Now next we have to calculate this shaded portion. We have 2 shaded portion, hence look at this shaded portion. So what it is? 13.2 minus 6.1 whole, okay, into thickness. The thickness is 11.4 into 13.2 minus 6.1 divided by 2 into 2, because there are 2 shaded portions. You can look at the calculation part. So now zpy will be 56.45 into 10 raised to 3. so once you have all this value, you can substitute this zpy in this equation, the top equation what you obtained, to get mdy. You will have 2 values, and in that you have to select the lower one. Now substituting in the design equation, you will get has 0.58, which is less than 1. okay, now once you do that, you will be checking for shear. What is the shear? Vd is equals to AVFI by root 3 gamma m naught, and this AV will be the area of the web, hence it is 200 into 6.1 into 250 divided by root 3 into 1.1 into 10 raised to 3. so it should be greater than your Vz. okay, hence your Vz is 14.3, hence it is greater, hence the selected section is safe under shear also. Now after that you will be checking for the final step, that is check for deflection. Now under deflection the load will be distributed uniformly, hence the equation to be used is 5 by 384 WL to the power of E I Z Z, and hence it should be, and also it should be less than L by 180. Okay, so L by 180 happens to be 25. Okay, and once you calculate all this, you are getting deflection as 6.16 mm. Okay, so 6.16 is less than 25 mm, hence it is safe. You can see the value substitute is 4.2 is your WDZ. Okay, W is equal to WDZ, L is equal to 4.5. When you substitute this, you will get 6.16. So the deflection is also under the control. It's less than the permissible values, hence it is safe.